Yeah, thank you. Thank you, Andreas, Timo, Matthew, Jed, like all the organizers. Like organizing something like this takes a lot of work, and I really appreciate you all joining forces to put it together. And I see that we have like, wow, more than 120 people in Zoom, like hello world. Rayon is one of the coolest libraries I've used. And when Timo emailed me about doing a talk, like it was clear to me that I wanted to do something that shows it. But one of the things that surprised me a lot afterwards was that many people were not really aware of it. So in this talk, we are going to be talking about doing data parallelism in Rust with Rayon, and we are then going to be applying it to a Lattice Boltzmann solver for computational fluid dynamics. So who am I? So I currently work at NVIDIA. I'm a GPU architect, where I work at the memory consistency and programming model of NVIDIA GPUs. I'm also a member of the C++ committee, working on concurrency and parallelism, and I tend to teach like parallel algorithms with C++ at supercomputing. I've been using Rust for a long time now. Like I've been using Rust since 2014, and there was a period of time from 2016 to 2020, 21, where I collaborated a lot on the Rust development. I worked a lot on CMD, like package features and packed CMD, and on safe code. Like on safe code guidelines, I was a maintainer of libc, which is how Rust interfaces with the operating system for a couple of years, and memory allocators. Yeah, before working at NVIDIA, I was in Aachen in grad school, and then I was doing computational fluid dynamics with HPC. So this talk kind of brings all of that together. So why do I care about like Rust for HPC or scientific computing? So the scientific software I encounter when working with developers typically has a very long and dynamic lifespan. Like PhD students come and go, implement some features, extend it here and there, and this happens over multiple decades usually. And the PhD students working on it are typically domain scientists for most of the software I work on. So it's very rare that I actually encounter computer scientists developing HPC software. And like the researchers using the software need to solve very large problems very quickly. And in modern systems, this means having to do parallel programming. But parallel programming is really hard. It's really hard to get well in practice. So some of the things like Rust excels are precisely solving these problems. So Rust has excellent integration with legacy software via C interfacing. It's pretty beginners friendly and safe. If a developer doesn't know the difference between the stack and the heap, it doesn't matter. Rust will protect them from having to know the details. It allows you to write high-performance software with performance comparable to C, C++, and Fortran, but without many of the pitfalls. And when it comes to parallel programming, Rust is thread safe. It means it rules out a huge class of mistakes that one can do when writing parallel code. And I really believe like Rust empowers domain scientists to write and evolve complex parallel software, and this is the main reason why I care about Rust. So moving on to Rayon and data parallelism in Rust. I've heard like there are a lot of non-Rust programmers in the audience, but I've also seen many expert Rust programmers in the audience. So I'm trying to strike a balance between both, but please like don't hesitate to interrupt me if there are any questions. So if you're new to Rust, like Rust has row loops. Here we have a variable sum and a loop with a variable I that goes from 0 to n. And in every iteration of the loop, we can access two arrays, x and y, multiply x with a scalar, add it to y, and we can do reduction type things like adding the current element of y to the sum. And so this is going to be modifying one element of this vector, and we're going to be modifying all elements of the vector y, and simultaneously we're going to be accumulating that result into a single variable. Another way to write this loop in Rust is like this. So Rust has iterators, so we can create a range of integers from 0 to n and obtain an iterator into that range. And then there are algorithms that operate on iterators, like for each, that will consume this iterator and that we can customize with a lambda. So for each will actually iterate over all elements of the range. And for every element, the operations inside this lambda will be performed. So this syntax with the two parallel bars is how you declare a lambda in Rust. And in between the parallel bars is where the arguments to the lambda appear. The lambda can capture variables from its environment, like a scalar a, references to the vectors x and y, and a mutable reference to this sum, so we can add to it. And this all works fine when we're writing sequential code. The iterators in Rust implement an interface called the iterator interface. And it declares things like the type of the items of the range, like what's element type is a range of integers in this case. And it has hundreds of methods, but essentially has methods for things like accessing the element, like next, to access the next element, and algorithms like for each that are customized with generic functions. What Rayon provides you is with an interface for parallel iteration. It provides an interface called parallelizer that comes with some methods like pariter. And this allows you to obtain a parallel iterator into some range. So in this case, we have obtained a parallel iterator into this range of integers. And then it comes with specialized implementations of the algorithms that run in parallel. So before we were running this loop essentially sequentially, and just by including Rayon and switching iter to pariter, we start running it in parallel. And that's the main advantage of Rayon. It's really easy to use. But many languages offer something like this, like C++, Fortran, like the international standards all have some form of parallelism in it, and we will see a little bit about that later. But in most languages, you need to make sure that the parallel code you have just written is actually safe. In this case, like the main question is it safe? Have we made any mistakes by changing our sequential iterator into a parallel one? And if we look at the lambda that we here, we're doing a reduction. We're modifying this variable sum. And before we were modifying it from one thread, but now we are adding to it from multiple threads. It turns out that this increment operator here is actually split. It's an operation that performs 3 steps. In the first step, it reads one value from memory, like the value of sum. Then it modifies a local variable with the update. And finally, it writes that value back to memory. So finally, it updates the value of sum. And if we have 2 threads, like these 3 steps can be, for example, interleaved by this when you're running on a real hardware. So it can happen like the first thread loads the value of sum, maybe initially it was 0. Both threads want to increment it by 1. So the first thread increments the local variable by 1. And at the same time, the second thread loads the value and it loads 0 again. And then at some time later, the first thread writes 1 to memory. And afterwards, the second thread writes 1 again. Right? So this thread writes 0. It increments 0 by 1, it gets 1, and then it's going to write 1. So we have 2 threads performing this operation, but instead of ending up with a sum of 2, we might end up with a sum of 1. So one of our increments got lots. And that's not great. And this is also one of the most common parallel programming bugs. So most programming languages don't want to regress optimizations that they do for sequential programs. So instead of trying to somehow define the language in such a way that this just works, what they define is like these programs are invalid. You're not allowed to write them. And this type of bug is actually called a data race. And it's one of the behaviors that are considered undefined in Rust. So what sets Rust apart from C++ and Fortran is that this type of parallel programming bugs actually fail to compile. You will get a compilation error saying you cannot modify sum here. You're not allowed to. And you can try to trick Rust with pointers and references and so on, and it will always fail to compile. Like there is no way to get this code to compile and save Rust and get that back. So this is the main thing that makes Rust special for parallel programming. So what can we do about this? One thing we can do is by using atomics. So instead of using an integer for sum, we can use an atomic variable that we can initialize to 0. And the main difference between an atomic integer and an integer is that atomics are internally synchronized. They will make sure that mutations from multiple threads are not lost. So if we instead use an atomic here and switch our assignment to an operation called fetch add, then we can fix this bug. And now we can modify the sum from multiple threads. However, this does not suffice to make this work because we're also accessing y and x in this loop, right? And it could be that we have a bug. We are indexing y from a different thread. So this index y is dynamic. And Rust cannot prove that dynamic values might not concurrently modify the same memory location. So it's pretty much the same issue as we have with sum, and we could fix it in the same way, just make all elements of y atomic, but there is a much better way. And that better way is to use something called an iterator adapter, like zip. So when working with iterators, beyond algorithms, we have other APIs that transform iterators into different iterators. So what zip does is zip takes two different iterators, in this case, x and y. We see like two arrays, one for x and one for y here. And it combines these two different iterators into a single iterator of pairs of elements. So instead of having just one element now, like the resulting type of this, the item type of this iterator is a pair. And for the first element of this range, the first element of the pair comes from the first vector, and the second element of the pair comes from the second vector, and so on. So by using zip instead of an integer range, now we don't have to index into the elements of the arrays inside the for each. And this enables Rust, like this will only compile if x and y happen to not point to the same memory location. And this is ensured by Rust like ownership rules. So the iterator that we're taking from x is a shared, like read-only iterator, while the one that we're creating from y is a mut iterator. It gives us exclusive access to one element of y. And now this code actually compiles, and it is all safe Rust, and it therefore runs correctly. So this will actually produce this right results for our vector y and for sum. But there is an even better way to write this than using atomics. So rolling on your own reductions with atomics is typically pretty complicated if you want to do it well. So instead of that, what we can do is we can use another iterator adapter called map to transform the pair of items into one single item. So as part of the map, we perform the vector update, and then we return just the result. And pick a different algorithm. Instead of for each, we pick a reduction algorithm like sum that will sum all the elements of y. And it knows how to do it in parallel. So this is not only simpler than using atomics, but it's also significantly more efficient. So here on the right, I have like the different versions that we have shown. So the sequential loop with iterators, sequential loop with zip. The parallel version with zip and atomics is here. I didn't forget about it. It just performs terribly. And finally, the one using the sum algorithm here. And this was measured on my laptop, Apple M1, has about 200 gigabytes per second of peak memory bandwidth. So you cannot really do better than that, just laws of physics. And the parsum version with Rust, it achieves about 84% of the theoretical peak, which is really, really good. So how does safe Rayon compare with other programming languages like C++ and Fortran? So as mentioned before, that C++ and Fortran have parallelism in the language. So C++ 17 added a parallel version of their algorithms, like there is a transform reduce algorithm that performs the same thing that Rust did. It works in a similar way. We have a map operation that modifies y and returns the value. And for the reduction, we use plus. It's more like similar to the default iterator algorithm in Rust. And Fortran 2008 added parallel loops with do concurrent, and Fortran 2023 added reduced clauses to perform reductions. So this actually looks pretty neat. I find it looks better than Rust and C++, to be honest. And I'm not a huge Fortran fan. So how do these three implementations compare to each other? And it turns out like Rust is pretty good. I had to run now in a different system, so the peak is no longer 200 anymore because of Fortran support in my Apple laptop. But on this system, C++ and Fortran are pretty much on par, but Rust is able to achieve almost 80% of a theoretical peak, which is also really, really nice. So we get not only similar or better efficiency than other low-level languages, but we also get safety on top, like parallelism bugs get diagnosed at compile time or latest at runtime. It's not like we just get garbage out and have to figure it out. So if you want to learn more about Rust and how to use Rayon, there is a talk by Nico Matsakis at the Raspberry conference in 2016. So Rayon is pretty old at this point. So it's been around for a long time. So it has excellent documentation. People are super friendly on GitHub. So if you have any issues, you can just ask questions there. And on top of everything that I've shown, Rayon has also APIs for building your own parallel algorithms. So if one of the 100 parallel algorithms that Rayon provides doesn't do what you need and you have to build your own, Rayon also has APIs to enable to do that in a safer way. And there are other types of data parallelism in Rust. Tomorrow, Miguel and Julie are going to be talking about portable CMD. So if you want to learn about that, don't hesitate to check out their talk. And I think Jed is going to be covering MPI a little bit in their computational mechanics of Rust talk. And if they weren't planning to do so, maybe they will do that now. So I think that was it for Rayon. So the results for toy problems like this are pretty good. But like, how does Rayon perform, and how is this to write like more complicated, like real HPC code with it? So a colleague of mine, Jonas, has a framework for parallel Lattice Boltzmann methods. Well, it has many frameworks for that, but has one that is designed to be an educational framework and also a framework that's used to test portable programming models for Lattice Boltzmann methods. It's written in C++ 17. It supports multi-core CPUs and GPUs using standard C++, and it simulates a three-dimensional cavity flow. So essentially, you have a box of fluid, and there is a velocity that's imposed on the top, and on the walls, we have just solid walls. So you end up with like a circular flow that goes like this. So a long time ago, like 2017, I wrote a Lattice Boltzmann solver with Rust using Rayon. And it picks one of the simplest possible Lattice Boltzmann algorithms. It's a two-population algorithm, so it has two separate arrays. It uses two times the memory that modern algorithms use. And it has something called split collision and streaming, which means it reads and writes to memory twice, also being about 2x slower than most of the modern algorithms. But the main advantage of this algorithm is like super easy to parallelize with Rayon. So that is what we are going to be looking at next. So the algorithm has two steps. One is collision. And collision, like the algorithm essentially performs a stencil computation. It reads values from one array and applies a function to them and writes them out to a different array. The collision operator is local. So we have a grid of cells, and each cell has multiple values. The collision operator reads the values of one cell in one array and writes to the values of that same cell on a different array. So this is quite easy to parallelize with Rayon. We have the output array here. We get a parallel iterator into it. In this case, I'm using the part chunks because I have to tile my grid into multiple values. And then I want to have a cbit with an iterator for the inputs where I'm going to be reading. And this doesn't have to be mutable. So all threads are going to be reading from the inputs, but for the outputs, each cell is only going to be writing to its local cell. And that's how we manage ownership and borrowing. And on top of this, I need to know which cell am I to be able to apply things like boundary conditions. So I'm going to zip that again with another iterator for that. And because Rust doesn't have variadics, this means that actually I end up with a tuple of elements where the first element is also a tuple. So I have a pair of elements for the first element of the pair, and then the index for the other elements. So to apply my boundary conditions, I just have to skip some cells. So I just use a filter to select cells that are not on my boundary. And then in this case, I can just use a for each to read my input array, compute some local array, and then I just write it back to memory. The second operation is a little bit more complicated. Basically, we are reading from elements for different cells, but you can write it in such a way that you still accumulate those into a single one. And this is what it makes this particular algorithm so easy to implement with Rayon. So because we can do essentially the same thing, take a part chunks iterator to the first array, zip it with, in this case, just indices, and then find out from which neighbors we have to read and write to the local array. And this is safe and it compiles because all threads can read from all inputs because no thread modifies it. But for the tricky part, which is the modifications, each thread is only allowed to see its local part. And yeah, using Jonas framework, I have a version of this algorithm implemented in it that I can compare with C++. And we see that for something more complicated, performance is most like on par. But what this means is like you get pretty much performance on par with other common low-level languages using high-performance computing, but with all the other benefits in terms of safety and productivity that Rust gives you. You don't have to debug race conditions at runtime for hours. Yeah. So to conclude, I think safe parallel programming is very attractive for scientific computing. Like most modern hardware in HPC centers is parallel. Rayon is a great resource in Rust, has excellent documentation, excellent performance, excellent functionality, has many parallel algorithms, and pretty broad platform support that allows you to write portable software. I haven't seen yet like a detailed evaluation of performance portability for HPC systems, like similar to what I did before about how much percentage of the peak do we achieve on all of these modern HPC systems. But on the systems I tried, the performance is excellent. And with respect to Lattice Boltzmann, like the simplest algorithms are very easy to implement. But as we move to more and more advanced algorithms, things become more challenging because there is no longer threads only write to one cell, but threads might have to write to different parts of multiple cells around them. And even though those are disjoint, expressing that with zip gets messy very quickly. You don't want to end up with 19 nested tuples of tuples of tuples that you have to process, right? So figuring out how to do things is still to be determined. And one main thing that's missing, me working at NVIDIA, like this is interesting to me, is that the ISO C++ and ISO Fortran code that I showed before actually runs on GPUs as is. Right? You just compile with a different flag and it will run on GPU. And this gives you a 10x performance improvement over CPU code. So currently, like there is no equivalent way to do that in Rayon today. So, and with that, yeah, I would like to thank you, and I'm happy to take any questions. And one more thing, if you are attending Supercomputing 2023, please reach out. Like it will be really nice to do a Rust gathering there. We have submitted a BOF to an event, but regardless of whether it's accepted or not, I think it would be really nice to meet anyways. Yeah.
Wonderful. Thank you, Gonzalo, for that really nice talk. So we've started to have some questions come through in the chat. So if anyone else has questions, throw them into the Q&A box. Then I've got time to ask a few questions. We'll get some nice thank yous coming through in the chat as well. So thank you from the audience as well as from me. So the first question we've had come through, does it make a difference how long the parallel threads run in Rayon? E.g., is it better suited to short-lived tasks like a GPU, or can you also run longer processes on them?
So that's a good question. I think Rayon keeps the threads alive. So it will, when you use it for the first time, it will keep a thread pool, like similar to what OpenMP does, where threads can do work stealing. And by design, it tries to adapt to how fine-grained your tasks are. But if you look at, let me see if I can go back. Oops. So if in the code I use something called part chunks, which basically allows you to chunk parts of the input. So if for whatever reason you don't want to process like one element per thread in the for each, you want to have more control to say I want to process 1,000, you can chunk your input with either this iterator or other options that Rayon has to control how elements are mapped to threads. So if you're doing something like one huge task, you probably want to dial that down manually.
Okay, thank you. And a question that's come through a couple of times, I think you touched on at the end, is about GPU support for Rayon. So do you know of plans, or are there any plans at NVIDIA or elsewhere to work on this?
I haven't seen anybody working on a GPU version of Rayon. Like there are many people working on GPU support in the ecosystem, from Rust GPU to, which has a SpeedV backend, to Rust CUDA, which has an MVVM backend. So you can write GPU code in Rust, but automatically dispatching something like Rayon to the GPU is pretty hard, just because you will have to be compiling from CPU and GPU code in the same binary and handling lambdas from the host and the device and detecting when you need to compile the device code. So if you wanted to have something that's as nice as ISO C++ today for that, which is single source, all code gets compiled only once, that will require quite a bit of compiler work. Things based on macros have been done and are possible.